In the 1960s and 70s, computer networks faced a total communication breakdown. Computers were built by manufacturers using entirely proprietary systems, meaning a machine from one company literally could not interpret the signals of another. IBM, for instance, built massive mainframes like the System 370. It was a closed ecosystem, engineered to communicate exclusively with other IBM hardware. Competitors like Honeywell utilized entirely different data formats and addressing schemas. A message sent from an IBM machine was noise to a Honeywell terminal, leaving early data networks fractured into isolated hardware silos. This fragmentation became a critical engineering bottleneck for research universities and the military. They needed a shared language to bridge these gaps, which led to the creation of ARPANET. In the 1970s, Vint Cerf and Bob Kahn solved this by developing a universal protocol suite. Instead of changing the hardware, they created a set of rules that ignored the physical differences between machines. The resulting internet functions as a philosophical and engineering triumph of interoperability, a logical layer that forces disparate hardware to speak a singular language. This language is TCP/IP. On January 1, 1983, it became the official standard of ARPANET, requiring every device on the network to adopt the protocol or face total isolation. The TCP/IP model organizes network communication into 4 distinct hierarchical layers: application, transport, internet, and network access. This stack relies on the separation of concerns. Each layer has a specific, isolated responsibility and only communicates with the layer directly above or below it. To understand this process, we will track the 300-millisecond lifecycle of a single HTTP request as it travels from a local browser to a Google data center. This hierarchical rulebook governs every bit of data currently in flight across the globe, providing the necessary scaffolding for the decentralized systems we will explore later. The process begins the moment a user types www.google.com into their browser. Immediately, the browser triggers a DNS lookup. Because computers route data using numerical IP addresses rather than names, the domain name system acts as a directory to find the specific machine hosting that address. At the application layer, the browser generates a block of application data. This layer focuses exclusively on formatting the raw payload, in this case an HTTP GET request, and defining what that data actually means. While the request is now perfectly formatted, it currently lacks any routing information or delivery instructions. To become viable for network transmission, this raw data must now descend the stack to acquire its packaging. The data drops into the transport layer, where it is broken into pieces and wrapped with delivery instructions. A TCP header snaps onto the front of the data, and the entire unit is relabeled as a segment. This layer requires a choice between 2 protocols, TCP for reliability or UDP for speed. UDP provides a connectionless, fire-and-forget approach, ideal for live video or gaming. However, web and financial data require the absolute reliability of TCP, which guarantees that every byte arrives in the correct order. This reliability is established through a 3-way handshake. Before data flows, the sender transmits a SYN packet. The receiver responds with a SYN-ACK, and the sender confirms with an ACK. Only once this logical connection is verified does the transfer begin. The transport layer ensures end-to-end delivery, abstracting the chaotic physical path the segment is about to take. The segment now descends to the internet layer. Here, an IP header is attached, containing the logical source and destination addresses, and the unit is relabeled as a packet. Routers across the internet evaluate this IP header at every hop. Each router makes an independent decision, directing the packet toward the next node in its journey. The packet reaches the final tier, the network access layer. Here, frame headers and trailers are added, finalizing the data as a frame. At this stage, the system injects a MAC address. Unlike the logical IP address, the MAC address is permanently burned into the device hardware, ensuring delivery across the local physical network. Finally, logical abstraction ends. The digital frame is converted into raw physical energy, electrical pulses, light, or radio waves, to be transmitted across the world. This complete encapsulation process turns a simple web request into a stream of physical signals capable of traversing the planet. When that signal arrives at a Google data center, the destination hardware receives the raw physical energy. The server now performs decapsulation. Moving up the stack, it strips away the frame, the IP header, and the TCP header, revealing the original, pristine application data. Google's web server processes the HTTP GET request and generates an HTML payload. That response then repeats the entire encapsulation journey back to the user. This intricate process of wrapping and unwrapping occurs flawlessly billions of times every single second. While TCP/IP is the working standard, networking literature often references the 7-layer OSI model. These models overlap significantly. In practice, the OSI's session and presentation layers are collapsed into TCP/IP's broader application layer. Engineers treat the OSI model as a theoretical taxonomy for the classroom, whereas the 4-layer TCP/IP stack serves as the pragmatic engineering reality in production environments. These same principles govern decentralized peer-to-peer networks. If we replace our HTTP request with a Bitcoin transaction, the underlying mechanics remain the same. Blockchain nodes do not use a proprietary physical routing mechanism. They establish standard TCP connections across the legacy internet to communicate. A Web3 wallet acts at the application layer, wrapping a signed transaction in TCP segments and using standard IP addressing to locate peer nodes. When a new block is found, it propagates outward through these synchronized TCP/IP connections. Each node receives, validates, and forwards the data until the entire network is updated. Bitcoin, Ethereum, and Solana operate as application layer protocols, riding directly on top of the established TCP/IP stack. Global interoperability exists because of the systematic encapsulation and layer separation established decades ago. Concepts like node synchronization and gossip protocols are built directly upon this TCP/IP foundation. To architect the decentralized future, you must first understand the protocols that move every bit of data today.